This lecture is about more on interpolation, the Z interpolation idea for solving a diversion equation, and high order discretization. So let's revisit one particular idea of the last lecture, which is when A is larger than 0. Again, we're talking about AUT plus AUX is equal to 0. Okay, so one perspective for the upwinding was that we need to figure out, here is J, here is time level n plus 1, time level n. We need to figure out what's the value here. We trace back along the characteristic line, right? So this point is that is xj minus a delta t, okay? Again, we have this thing. It's dx dt is a, so here is 1, here is a, right? And we know here is delta t, so that's xj minus delta t, and that's the location j minus 1. Okay, so the upwinding is, as we talked about last time, what the idea is that it approximates u at xj minus a delta t at tn by a linear interpolation. So this is exact guide, so which we don't have. So we do it numerical approximation. Here in particular, we took a linear interpolation between xj minus 1 and the corresponding value is uj minus 1 n, right, time level n, and xj uj n, right, location and the function value. So you write a point slope form, then you evaluate at xj minus a delta t, you get exactly the upwinding scheme. You revisit last video, okay? And also we derive the stability condition, which is you need, loosely speaking, you need this xj minus a delta t is between xj minus 1 and xj. So which means the condition for delta t is that a delta t over h is less than 1. That's for the case A is positive. So the question that we ask ourselves is that, can we, it is an interpolation, right? So it is a linear interpolation. So here is the linear interpolation. The question is, can we do better? Can we use, for example, a grid xj minus 2, xj minus 1, xj, right? And of course, the corresponding values, you need the location and function value, which is uj minus 2n, uj minus 1n, ujn, to do a quadratic interpolation to approximate the same unknown guy, uxj minus a delta t at time level tn. So that's pretty easy to do. We just do what we do in 361. We come up with a quadratic polynomial, in terms of x. So we will have the u of xj minus a delta t tn, right? This will be equal to you have this uj minus 2n times, what's that, x minus xj minus 1, x minus xj divided by negative h, and then negative 2h, you plug in xj minus 2, right? Using the characteristic polynomials, plus uj minus 1n times x minus xj minus 2 times x minus xj divided by, you plug in xj minus 1, you get negative 8, positive h times negative h, plus finally ujn, you have x minus xj minus 2, x minus xj minus 1, h, 2h. Alright, and then you evaluate and then evaluate at xj minus a delta t. Right, well, here we're going to take a slightly different, a quicker approach for our setting, so we can see easily the particular meaning of what we are going to derive, right? So if we let's see, if we do a little transformation, if we define y, which is x minus xj minus 1 divided by h, all right, then what do we have? Then we have xj minus 2, xj minus 1, xj, this will become, for y, right? For y, if you plug in xj minus 2, you get y is negative 1. So negative 1, 0, and 1 for y. Let's do the trick. Then you're going to have a function value u negative 1, you get uj minus 2, and 0, you get uj minus 1, and 1, you get ujn, right? So the quadratic function would be then ay squared plus by plus c. We know when y is 0, you should get uj minus 1n, so that's c. And then you plug in y is 1, you get a plus b is equal to plus uj minus 1 is equal to ujn, right? You plug in negative 1, you get a minus b plus uj minus 1n is equal to uj minus 2n. So we get that a is equal to, you add the two equations and divide by 2, okay? So you're going to get 1/2 uj minus 2 uj minus 1n plus uj minus 2n, right? And b is you subtract the 2 and divide by 2. Okay, so which is ujn minus uj minus 2n divided by 2. Because uj minus 1n cancel with each other as you subtract the two equations. So there you go. So we know that the u xj minus a delta t tn, this can be approximated by this quadratic polynomial, which is a is 1/2 ujn minus 2 uj minus 1n plus uj minus 2n. This guy times my y squared. What is y? Y is h x minus xj minus 1 squared. Alright. Plus b, which is ujn minus uj minus 2n times my y, which is h x minus xj minus 1, plus my c, which is uj minus 1n. Okay? And I need to evaluate the whole thing at x is equal to xj minus a delta t. So that's easy because once you plug in that, for a, we know this xj minus a delta t, alright, that's our x. This minus xj minus 1 divided by h, that's xj minus 1 is equal to h, so you get 1 minus a delta t over h. That's our lambda, right? If we call that lambda, you are going to get 1/2 ujn minus 2 uj minus 1n plus uj minus 2n times 1 minus lambda squared plus ujn minus uj minus 2n divided by 2 times 1 minus lambda plus uj minus 1n. Okay? So this is our lambda. Okay? We can easily simplify this. So which is our new scheme, which is u j m plus 1, all right? This is approximation to u xj minus a delta t at time of n, but we traced back along the characteristic line. So this is going to be equal to well, 1 minus lambda squared. Okay, so you're going to get 1/2 lambda squared, all right, times that ujn minus 2 uj minus 1n plus uj minus 2n. Okay, and the lambda term, so we have minus 1/2 lambda. All right, you're going to get, there's a 1 minus 2 lambda there, so there's 2 ujn minus 4 uj minus 1n plus 2 uj minus 2n, right? Take care of the first term. The second term is you have automatically this ujm minus uj minus 2n, right? Plus the constant term, a little bit messy, but it's okay. You get 1 from the 1 minus lambda squared, and 1/2, you have this uj n minus 2 uj minus 1n plus uj minus 2n, right? Plus the 1 here, so you have plus ujn minus uj minus 2n plus a constant term there, so you have plus 2 uj minus 1n, alright? So we see that minus 2 plus 2 cancel, and then uj minus 2, uj minus 2 cancel. Okay? And we get 2 ujn left. We divide by 2, you get ujn. So that's nice. That's like the forward Euler term. Okay? And then we have this the linear term, 1/2 lambda. You simplify, you're going to get 2 ujn plus ujn, you're going to get 3 ujn, right, minus 4 uj minus 1n, uj minus 2, you get 2 minus 1. So it's plus 1 uj minus 2n, right? And then you have this plus 1/2 lambda square left, which is ujn minus 2 uj minus 1n plus uj minus 2n. Okay? So that's our scheme, ujn plus 1, right? If we rewrite this, you see clearly how that's related with what we had before. again, the lambda is just a delta t over h, alright? So that is to say my ujn plus 1 minus ujn divided by delta t, okay? This is we are moving ujn to the left divided by delta t, so we have h left. So we have negative a, right? We have 2h and 3 ujn minus 4 ujn minus 1 and plus uj minus 2n, alright? Plus, you get a 1/2. You have a squared delta t squared. We divided by delta t, we have 1 delta t left. So you get a squared delta t. It was delta t squared, but again, we divide by 1 delta t. And then let me put h squared here. You get ujn minus 2 uj minus 1n plus uj minus 2n, right? So if you recall what we did when we studied the d plus d minus d0 at the very beginning. So this guy is basically ut, right? This is just negative a u x, actually. It's a order 2 approximation for ux, one-sided. And this is just, of course, some epsilon times uxx, okay? So we go back, that's our epsilon. And if you recall, that's actually equal to Lax-Winthrop, epsilon Lax-Winthrop. So that's a modified scheme for this particular, modified equation for this particular scheme. And we introduce a little bit of viscosity, the same amount as Lax-Winthrop, and we have a order 2 scheme, order 2 in space. That's also upwinding because we are using the guys on the left. You are using xj minus 1, xj minus 2. You are using the ones on the left when a is larger than 0, right? So this is there's an actual name for this. This is the so-called beam warming scheme, which is like a second order upwinding. Again, it's upwinding because this is, we're talking about the case when h larger than 0. We use j minus 1 and j minus 2 to approximate ux. So this particular approximation, that's order 2, and this approximation is, as we know, order 2. So second order in space, second order upwinding. Another way to understand, to derive this scheme, which better shows its relationship with the Lax-Winthrop, to another way to derive this beam warming, we're going to call that BW scheme. All right, so we're going to mimic the Lax-Winthrop. Remember, what is the Lax-Winthrop is that it is doing a Taylor expansion along time. So we have ujn plus 1. All right. So this, because that is to approximate u at xj tm plus 1. But what's tm plus 1 is tm plus delta t. All right. So this is like ujn, right, plus delta t times ut plus 1/2 delta t squared times utt, right? What we then use is that ut is equal to negative aux, okay, because that's from the equation, and utt is becoming a squared uxx. You take another time derivative, then you use the equation again. Okay, so the reason is that is UTT is negative AUX. Let me repeat this. This with another t, and this is negative A UT of x, but we know UT, which is negative A times negative AUX x, which becomes A squared UXX. Alright? So this then is UJN minus A delta T UX plus 1/2 A squared delta T squared UXX. Okay, UXX. And now that's just UJN plus 1 minus UJN divided by delta T is negative AUX plus 1/2 A squared delta T UXX. Alright. So you already see that's our epsilon. We're adding epsilon amount of UXX to the equation. So then if you use, it all depends how you discretize this term. Okay, so if you use what we did for the Lex-Windroff, we have what? We have uj plus 1n minus uj minus 1n divided by 2h to approximate ux. Then we have the Lex-Windroff. Okay, now we just showed above. If you use 2h 3ujn, right, minus 4 uj minus 1n plus uj minus 2. What do we had above? uj minus 2n to approximate ux when a is larger than 0. When, and the other guy, right, which is we also did it in homework, which is negative 3 ujn, you have plus 4 uj plus 1n minus uj plus 2n to approximate ux when a has a negative sign. That's the essence of upwinding. When depending, you look at the sign of a. When a is larger than 0, the wind is blowing from left to right. So you use 2 points on the left. When a is less than 0, the wind is blowing from right to left. Okay, so then you use 2 points on the right, which is aj plus 2 and j plus 1. What do we have here is that is the beam warming, right? Beam warming that we just arrived above. For the above, we derived the case H is positive. When it's negative, it's very similar. You will see it boils down to use this guy.